Welcome to our comprehensive guide on Kotlin coroutines. In this video, we'll explore the most important concepts, interview questions, and practical tips for mastering coroutines in Kotlin. Coroutines are a powerful tool for writing asynchronous, non-blocking code, making them essential for modern Android development. Whether you're preparing for an interview or just want to deepen your understanding, this video will walk you through everything you need to know, starting from the basics and moving into advanced topics. Let's dive in and discover how coroutines can transform your coding experience. Coroutines are Kotlin's native solution for writing asynchronous and non-blocking code. They allow developers to write code that looks sequential and traditional, but actually leverages suspending functions and structured concurrency. This means you can handle tasks like network requests or database operations without blocking the main thread, making your apps more responsive and efficient. Coroutines simplify complex asynchronous programming, letting you focus on logic rather than thread management. Threads are managed by the operating system and can be expensive in terms of memory and context switching. Coroutines, on the other hand, are lightweight and can be multiplexed on fewer threads. This allows for efficient concurrency without the overhead of explicit thread management. Coroutines provide a more scalable and manageable way to handle multiple tasks simultaneously, making them ideal for modern applications. In Kotlin, coroutines are created using the launch or async builders. The launch builder is used for fire-and-forget style coroutines, while async is used when you need to return a result. Both builders require a coroutine scope, which defines where and how the coroutine will run. This approach allows you to start concurrent tasks easily and manage their lifecycle within your application. A coroutine scope defines the lifetime and cancellation of coroutines. It provides the context in which a coroutine runs, often tied to the lifecycle of a component like an activity or view model. Managing coroutine scopes ensures that coroutines are properly canceled when no longer needed, preventing resource leaks and improving app stability. Suspend functions are the building blocks of coroutines. They can be paused and resumed later without blocking the thread. Suspend functions can only be called from within a coroutine or another suspend function, enabling sequential and structured synchronous programming. This makes it easier to write code that looks synchronous but is actually non-blocking. Dispatchers provide the context for coroutine execution, defining the thread or thread pool on which the coroutine will run. Common dispatchers include dispatchers, main for UI operations and dispatchers, I/O for I/O-bound tasks. Choosing the right dispatcher ensures that your coroutines run efficiently and don't block important threads. Structured concurrency is a pattern that ensures proper handling of coroutines by enforcing the cancellation of child coroutines when their parent is canceled. This prevents resource leaks and guarantees that all coroutines within a scope complete successfully or are canceled together. Structured concurrency makes managing concurrent tasks safer and more predictable. Exceptions in coroutines are propagated up the call stack by default. To handle exceptions, you can use try-catch blocks within a coroutine or set a global exception handler using coroutine exception handler. Proper exception handling ensures your app remains stable and errors are managed gracefully. The launch builder is used for fire-and-forget coroutines that don't return a result, while async returns a deferred object representing a future result. Async allows you to perform concurrent computations and retrieve results later, making it ideal for tasks that require a return value. Coroutines can be canceled by calling the cancel function on the corresponding job object or by canceling the associated coroutine scope. Cancellation is cooperative, meaning the coroutine code should periodically check for cancellation using the isActive property and gracefully stop its execution. Launch starts a new coroutine and returns a job object immediately without blocking the current thread. It's used for fire-and-forget coroutines. Run blocking, on the other hand, blocks the current thread until the coroutine inside it completes. It's mainly used for tests or top-level coroutine code. To prevent blocking the main UI thread, long-running coroutines should be executed on a thread other than the main thread. You can use dispatchers, default or create a custom thread pool with newfix thread pool context. This ensures your app remains responsive during intensive operations. Coroutine context is a set of elements that define the behavior and context of a coroutine, such as dispatcher, exception handler, and other context elements. It is represented by the coroutine context interface and is propagated from parent to child coroutines, affecting their execution. With context is a suspending function that allows you to switch the coroutine's context to a different dispatcher. It suspends the current coroutine, switches to the specified dispatcher, executes the provided block of code, and then resumes the coroutine in its original context. Coroutines provide protection against race conditions by executing code sequentially within a single thread or dispatcher. If shared mutable state needs to be accessed concurrently, synchronization mechanisms like mutex or atomic types can be used to ensure thread safety. Coroutine cancellation is a cooperative process, allowing the coroutine to clean up resources and stop execution gracefully. Thread interruption is an abrupt signal sent by one thread to another, which can lead to resource leaks and abrupt termination. Coroutines offer safer cancellation mechanisms. You can use with timeout or null functions to specify a timeout for a coroutine. With timeout throws a timeout cancellation exception if the timeout is exceeded, while with timeout or null returns null instead of throwing an exception. This prevents coroutines from running indefinitely. Structured concurrency helps manage the lifecycle and cancellation of coroutines by ensuring that child coroutines are canceled when their parent is canceled. This prevents resource leaks and ensures all coroutines within a scope complete or get canceled together, providing better control and reliability. Coroutines propagate exceptions up the call stack by default. If an exception occurs in a coroutine, it will be propagated to the parent coroutine or the coroutine scope. To handle exceptions, use try-catch blocks within coroutines or set a global exception handler using coroutine exception handler. Coroutine channels provide a way for coroutines to communicate by sending and receiving data in a non-blocking manner. Channels can be used for producer-consumer patterns, stream processing, or any scenario where coroutines need to exchange data. There are different channel types, each with unique characteristics. Sync is a coroutine builder that returns a deferred object, representing a future result. It allows concurrent execution and provides a way to retrieve the result later using await or other deferred functions. This is useful for tasks that need to run in parallel and return results. Structured concurrency ensures that all coroutines within a scope complete or get canceled together. This helps manage resource cleanup by automatically canceling and releasing resources associated with coroutines when they are no longer needed, improving app stability. Coroutine scopes define the lifetime of coroutines and manage their cancellation. They provide a structured way to launch and manage coroutines, allowing for better control and organization of concurrent tasks. Proper scope management is key to robust coroutine usage. Coroutine builders are functions that create and start coroutines. Common builders in Kotlin include launch, async, run blocking, and with context. Each builder serves a specific purpose, allowing you to tailor coroutine creation to your needs. To ensure thread safety when working with shared mutable state in coroutines, use synchronization mechanisms like locks, mutexes, or atomic operations. Kotlin's mutex and atomic types are designed for this purpose, preventing race conditions and ensuring safe concurrent access. Coroutine dispatchers determine the thread or thread pool on which a coroutine will be executed. Dispatchers specify the context in which a coroutine runs and handles switching between threads. Common dispatchers include dispatchers, default, dispatchers, I/O, and dispatchers main. In coroutines, errors can be handled using try-catch blocks or coroutine exception handler for global exception handling. You can also use supervisor scope or supervisor job to isolate failures of child coroutines, preventing them from affecting the parent coroutine. Coroutine flow is a reactive stream processing library in Kotlin. It represents a stream of values asynchronously and sequentially, combining the benefits of coroutines with reactive streams. Flow supports structured concurrency and cancellation, making it ideal for handling data streams. Launch returns a job object representing the coroutine's lifecycle, allowing you to manage and cancel the coroutine. Async returns a deferred object representing a future result, which can be retrieved using await or similar functions. Cancellation in coroutines is cooperative. You can handle cancellation by periodically checking the isActive property or using functions like ensureActive or yield to check for cancellation points. Setting timeouts with timeout or null also helps manage cancellation. Launch does not return a result directly, as its main purpose is to perform fire-and-forget style coroutines. It returns a job object for lifecycle management. Async returns a deferred object, and its result can be obtained by using await on the deferred object. When using async, exceptions are deferred and wrapped inside the deferred object. To handle these exceptions, use deferred await inside a try-catch block to catch any potential exceptions and handle them accordingly, ensuring robust error management. Coroutine context propagation refers to the automatic propagation of context elements from a parent coroutine to its child coroutines. This ensures child coroutines inherit the same context, including dispatchers and exception handlers, maintaining consistency. To cancel a group of related coroutines, create a coroutine scope using coroutine scope or supervisor scope. When you cancel the scope, all coroutines launched within that scope are canceled, ensuring proper cleanup and termination. The yield function is used to suspend a coroutine, allowing other coroutines to run. It's similar to cooperative multitasking, where a coroutine voluntarily yields its execution to give other coroutines a chance to execute, improving concurrency. Structured concurrency promotes launching child coroutines within a parent coroutine scope. When using nested coroutines, the parent waits for all its child coroutines to complete before it completes itself, ensuring proper cleanup and cancellation. Coroutines handle blocking operations by using non-blocking alternatives or moving the blocking operation to a separate thread or dispatcher. This allows the coroutine to suspend its execution and let other coroutines continue running, improving efficiency. The coroutine scope interface defines a scope within which coroutines are launched and managed. It provides coroutine builders like launch and async, and allows for cancellation and structured concurrency by providing a coroutine context and a job object. Timeouts for coroutines can be handled using with timeout or null functions. With timeout throws a timeout cancellation exception if the timeout is exceeded, while with timeout or null returns null, preventing coroutines from running too long. Coroutine cancellation propagation refers to the mechanism by which cancellation is automatically propagated from a parent coroutine to its child coroutines. If a parent coroutine is canceled, all its child coroutines are also canceled, ensuring proper termination and resource release. The coroutine exception handler interface is used to handle uncaught exceptions within coroutines. It provides a way to define a global exception handler, allowing centralized management of errors thrown from coroutines. Ordered execution of coroutines can be ensured by using sequential composition operators like await and invoke on completion. These operators allow you to define dependencies between coroutines, ensuring they execute in a specific order. The function converts a collection, iterable, or other types of objects into a coroutine flow. This allows you to transform synchronous data sources into asynchronous streams, which can be processed using coroutine flow operators. Structured concurrency ensures exceptions are properly handled within the context of the parent coroutine. If an exception occurs in a child coroutine, it is propagated to the parent, allowing for centralized exception handling and cleanup. You can limit the number of concurrent coroutines using a semaphore-based mechanism. By using a limited-size semaphore or a custom coroutine dispatcher, you control how many coroutines run at the same time, preventing resource exhaustion. The flow-on operator specifies the dispatcher on which downstream operators of a flow should run. It allows you to switch the execution context of the flow, ensuring that downstream operators execute on a specific dispatcher for optimal performance. Multiple coroutine flows can be combined using operators like zip, combine, flatten concat, or flat map concat. These operators merge values emitted by multiple flows into a single flow, enabling complex data processing scenarios. Cold flow starts emitting values only when a terminal operator is applied, and each collector receives the same set of values. A hot flow emits values regardless of collectors, and new collectors receive values emitted after they are added. Understanding this distinction is key for stream processing. Backpressure in coroutine flows can be handled using operators like buffer, conflate, or collect latest. These operators control the rate of emission and consumption of values, preventing overflow or slowdowns due to backpressure. Coroutine cancellation scopes, defined by the coroutine scope interface, allow you to create a scope within which coroutines are launched and managed. When the scope is canceled, all coroutines launched within it are canceled, ensuring proper cleanup and termination. Coroutines have become a fundamental part of modern Android development. Understanding coroutines is crucial for Kotlin Android developers, as they simplify asynchronous programming and improve app responsiveness. Mastering coroutines will help you build robust, efficient, and scalable Android applications. By familiarizing yourself with these coroutine interview questions and their answers, you'll be well prepared to showcase your knowledge and proficiency in coroutines during interviews. Keep practicing and exploring coroutines to become a confident and skilled Kotlin Android developer. We've covered the top 50 Kotlin coroutine interview questions, ranging from basic concepts to advanced techniques. Continue practicing experimenting, and applying these concepts in your projects. Coroutines are a powerful tool, and mastering them will set you apart as a developer. Thanks for watching and good luck with your Kotlin journey.